Basically, today I'm going to discuss a tiny part of chemical reactions, and basically we will ask ourselves some questions and briefly discuss about some topics or terms which is really important to uh, know to understand the chemical reaction dynamics. But fortunately or unfortunately, that those topics are not really popularly known in the chemistry community. And basically, I'll discuss some rate theories, which we call statistical rate theories, and then I will discuss the energy transfer in molecules and briefly about the non-statisticality. Okay, so uh, chemistry is basically we know the chemical reactions, which is the making or and the breaking of chemical bonds, and the rate at which they do so, right? So if we understand the rate and how the molecules react to form product, then we can actually control the dynamics of molecules. We can we can play with the molecules actually. So the rate and mechanism is very important to understand first. So let's first look at the rates of how do you compute rates of any chemical reactions. So first to compute rates, so we basically use the popular theory is actually transition state theory, right? So we use this theory in our daily basis. So let's first discuss this. Okay. So the full name is transition state theory. So I'm not discuss much detail about the derivation because of two reasons. So basically, it will consume significant of our discussion time, and reason number B is here parallelly there is a full course is going on, so you can gain knowledge of your lifetime from there. So at least in these topics. So transition state theory, there are some great names associated with this theory. So Eyring, starting from the Arrhenius, then Eyring, Pollack, Huygens, Pechukas, etc. And there is so many names associated with this theory. So basically in TST, let's first start two reactant molecules A and B. So they are going to react and form a and kind of activated complex, say AB star or AB double dagger. Then this activated complex will transform into product T, right? So the main approximation is idea is that first the reactant molecules actually come together and they form an activated complex. Then this activated complex will transform into product. So I will mainly discuss the Eyring derivation briefly. So Eyring actually assumes that there is an activated complex. Let's say this is the bottleneck region. That means this is the dividing surface, which is dividing the reactant side and the product side. So this is the reactant side, and this is the product side. And this is activated complex, which is called the bottleneck region. And there is some length scale associated with this region, right? Which is delta. Because there is some length scale associated with the activated complex also. So which is delta. And so in the Eyring's theory, the main approximation or assumption was that once the trajectory cross this bottleneck region, then there is no coming back. So once the trajectory cross this region, then we are assuming that the reaction is reaction happens. Okay, so there is no recrossing. So this is the important assumption in this theory. So there is no recrossing. But how do we know the trajectory won't come back? So this is a very poor assumption that once the trajectory cross this barrier region or bottleneck region, there is no coming back. So Eyring actually thought that to compute the rate, so rate is basically the probability of this activated complex to go from this side to this side, right? And times the concentration of this activated complex. So this was the Eyring's idea. So to first compute the probability, like probability of activated complex to go from left side, from the reactant side to the product side. So probability is basically, it will be 0 to infinity. Like at time dt, then e to the power minus beta p square divided by 2m dp. Then normalized with 0 to delta, sorry, 0 to delta, because that's the length scale. Then it is minus infinity to infinity, whole range of momentum dp e to the power minus beta p square divided by 2m, right? So look at the numerator here. So numerator, the range is 0 to infinity. Why 0 to infinity? Because the trajectory has to cross from this side to this side, right? That means we are assuming that this is negative momentum side and this is the positive momentum side. So momentum has to go from 0 to infinity, means all those trajectories having positive momentum, we are considering that. That's why the limit is 0 to infinity. And in the denominator, the whole range of momentum, we are normalizing it, like minus infinity to infinity. If you just do the derivation, I'm not doing the derivation here. So if we just do the derivation, it will come back as dt times 1 upon beta. So beta is the inverse temperature, then delta, then root over 2 pi m by beta. So basically it will be dt divided by delta times root over 2 pi m beta. So this is the probability of that activated complex or trajectories from going from reactant side to product side. Now to calculate the rate, so we have to just multiply this probability with the concentration of the activated complex, right? So let's say the concentration is star. So delta.
Shubhadeep,
Oh, okay.
what was this delta term?
Delta is the length scale associated with the activated complex. Let's say, so reactant was A and B, right?
Mm-hmm.
A and B will first come together and form kind of activated complex. So let's say activated complex will look like this.
Mm.
So a complicated structure of this complex. So this is, let's say, AB double dagger. Now there is length scale, means this length. What is happening? Length scale means this length scale. The length scale associated with that activated complex, which is delta.
The length scale associated with this activated complex.
Or you can say the bottleneck region, because okay, crudely, if you see one-dimensional potential energy surface, then this is the reactant, this is the product. Here you see this first index 1 saddle point, which you call the transition state, right? This transition state or the dividing surface, you call it. But this is not a particular point. Here we are considering that the length scale associated with the activated complex is equal to the length scale associated with this bottleneck region. We are considering this as a region.
Okay.
This is delta.
Okay.
This whole bottleneck region is called delta. We are just
So if they are in the integration in the denominator, Their other variable is missing here. I think this is dx or dr. It's just small
Yes,
mathematical thing. Yes, yes.
DQ. This is DQ,
Given.
and so rate will be just the probability 2 pi m beta times the concentration times the probability, which will be this. So rate basically probability per unit time. So probability divided by dt. So that's why the rate will be just concentration times the divided by delta times 2 to the power 2 pi m beta. Now here I think what did that.
Subhadip,
Yes.
yeah, so whenever we draw some potential surface, in the x-axis there is some CV.
Yes.
So whenever telling that there's a length scale or length scale of that bottleneck region. So what's like in which dimension the length scale is in? Is it some dimension of like it is not a length per se,
No.
but then so which this what are the unit or like what's the quantity delta actually is?
Yeah, delta is actually to basically cover our ignorance about the activated complex. So when Eyring was doing this derivation, he didn't have any proper or actual accurate idea about how the activated complex will look like, right? So activated complex is some sort of complex. So then he approximate this activated complex that there is a bottleneck region around that index 1 saddle point. So let's say this is the index 1 saddle point or
No,
transition.
I'm asking the bottleneck region in which space? Like what's the space
It is in the
consistent?
configuration space. It is in the configuration space.
Oh, okay. Got it. Okay.
In the multi-dimension case, you can also visualize it is in the configuration space.
Okay. Fine, yeah.
So now at this point, I think actually compare this microscopic formula. This is all microscopic formula, right? So this microscopic rate formula with the macroscopic rate equation. Like in the chemical kinetics, we know that rate is equal to just some effective constant times the concentration of reactant molecules. Yeah. So I didn't actually compare these two microscopic term and the macroscopic term here. So basically now the rate constant Kf will be equal to the concentration of that activated complex divided by concentration of the reactant molecules times 1 upon delta to the power of 2 pi m beta. So this will be the effective rate constant. Now look at this expression. In this expression, we don't know what is delta. Like accurately don't know what is delta. We are just assuming a region delta. We don't know anything about delta. We don't know the activated complex, what it's look like, and like mass, etc. We don't know the mass of the activated complex. So there are many unknown quantities in this expression. But ultimately, so again, now at this stage, okay, let me just draw. So this is, let's say, one-dimensional, a particular reaction coordinate or CV, and this is the activated transition state or activated complex. And there is, let's say, there are many orthogonal regions also here, okay, at the transition state. So I think actually here actually what it did at the transition state. So total Hamiltonian he actually separates into two terms. One is the translational motion around the reaction coordinate, which is this motion. So trajectories are translating from left side to right side, which is the translational motion along the reaction coordinate. So just the kinetic energy term is 20 plus divided by 2n. Plus all the potential, all the H double dagger, which is the energy of this activated state plus all those orthogonal states. Okay, so which is the H double dagger term. So he actually separates these two terms. So this is called the assumption of separability condition in the transition state theory. So this, what does this mean? This means that translational motion along the reaction coordinate don't talk with the all those orthogonal modes. That means they are totally separable. So this motion is not talking with all other these orthogonal modes. That means there is no energy transfer between these orthogonal modes and this translational motion along the reaction coordinate. So this is the second assumption. So first assumption was that once the trajectory cross the barrier, then there is no coming back, there is no recrossing. So there is no recrossing actually. And the second assumption, the assumption of separability. So there is no energy transfer between the orthogonal modes and the motion along the reaction coordinate. Now, if you use some StatMech, and ultimately you can get the rate constant K effective, which will be equal to just K double dagger divided by Q double dagger. Q double dagger is associated with these orthogonal terms. From the statistical mechanics using partition function, you can get that in this expression. Q double dagger by QA QB times KBT divided by H times e to the power minus E double dagger divided by KBT. Okay. So this is the expression you get from the Eyring derivation, Eyring's theory. So H is the Planck constant. Now you can ask, this is the classical theory, what the H is doing here. Planck constant you generally see in the quantum mechanics, but this is all classical theory, classical statistical mechanics, classical derivation. So what H is doing here? So it is an important question to ask. Think about yourself. Think this question also. So Kb is the Boltzmann constant, T is the temperature, and E double dagger we call the activation energy or energy threshold. Right. All the quantum mechanical interaction between the reactant molecules, like in the activated complex, all those tiny microscopic interactions, all things are hiding in this term, activation energy. And Q double dagger is the partition function of the activated of the orthogonal modes, right? Partition function of the orthogonal modes at the transition state. So QA, QB are the partition function of the reactant molecules A and the reactant molecules B. So what's the magic here? Why we use this equation in our daily basis? Because it is elegant and it is easy to use. Why it is easy to use? Because we don't have to know much information about how the chemical reactions is happening. If we know about the transition state, just the transition state, that means index 1 saddle of the potential energy surface. So we can then calculate the Q double dagger. That means the partition functions of the other orthogonal modes at the transition state. We can easily calculate the partition function of reactant molecules QA and QB on the basic statistical mechanics. And using the ab initio, like Gaussian electron structure computation, you can get the E double dagger. So just by getting the information about the transition state and the reactant molecules, you can get or you can find out the rate of chemical reaction. So you don't have to know how the reactant molecules are reacting, and from this state to this state, how it is going, you don't have to know. So that's why people use the transition state theory very often, because we don't have to know much information about the chemical reactions. But there is some pitfall also, I will discuss it later. So so basically there are at this stage, transition state first approximation was there is no recrossing. Second assumption was assumption of separability. Means there is no energy transfer between the reaction coordinate and the orthogonal modes. So basically at this stage, we are assuming there are no dynamics, right? This is crucial. So this is the three assumptions of transition state theory at this stage. Now Now for one-dimensional case, for if you just solve this for one-dimensional case, you will get Kf equal to, so basically 1 upon root over 2 pi in beta times e to the power minus beta e double dagger. So this is the rate constant per 1D case. So just,
Subhadip,
yeah.
so how the recrossing and separability, like no recrossing and separability is translating to no dynamics, like how are you getting this no dynamic part? Can
No
you explain a bit
dynamics
more?
because so basically recrossing free transition state means we are neglecting dynamics, right? Because let's say this is the potential energy surface along one-dimensional reaction coordinate,
Mhm.
and there is the trajectory you start from here. Okay.
Mhm.
So trajectory is spending too much time here, then it is going like here. Then once this is the transition state, dividing surface, once it is crossing, we are telling that the reaction is happening. Like trajectory is going from reactant side and product side, right? This is the assumption of TST.
Mhm.
But after this point, instead of going back at the product side, the trajectory can it can do like this, right?
Mhm.
Then it can come back in the reactant side.
Mhm.
This is the actual dynamics, let's say, of the trajectory, the yellow one, and the black one is the assumption of TST. So the recrossing free TST means we are neglecting the dynamics.
No, we're neglecting the dynamics in one side. But like we're constraining that it cannot come back. But the dynamics can still happen on the other side of the barrier.
No, neglecting dynamics means this trajectory, according to the TST, we are calling it the reactive trajectory. Means this trajectory is crossing is going from reactant to products. Okay. But actually, this trajectory is not a reactive trajectory.
The yellow one you're talking
about. Yeah.
Yeah.
So this trajectory is not a reactive trajectory, right? Because it is not forming product. But according to TST, this trajectory is forming product. Because once it is crossing this region, we are assuming that the reaction happens.
Yeah, but then we are still taking into consideration the dynamics. We're not throwing all the dynamics, are we?
Yeah, we are throwing all the dynamics here. All the dynamics we are throwing here, because once this assumption is there, once it is crossing, then the reaction is happening. But actually, in proper dynamically, what is happening? The trajectory is going, but again it is coming back, right?
Yeah.
So that's why we are throwing away all the dynamics here.
No, if it is crossing, in real case, then it can go into the product or it can come back.
Yes.
We are like discarding the possibility of coming back. That's the constraint that we are taking, exactly. But then how does that translate into we are just ignoring all the dynamics?
All the dynamics mean those trajectories after recrossing, those trajectories going into the product side, that is fine. Those trajectories are fine. But for those trajectories after recrossing, which are coming back, which are recrossing, let's say again it can recross. Like it can do like this.
Yeah.
So for those trajectories, we are neglecting dynamics. Right?
Okay. Got it.
Because we are overcounting these. First, let's say for this trajectory, the reaction is happening at this point, according to TST. Again, it can recross here, and then again it can recross here, right?
Okay, got it.
Here also,
so once it's crossed, we are not interested into the dynamics.
No, once it crossed, we are not interested in the trajectory dynamics.
Yeah.
Subhadip,
yeah.
The 3 points you have written: recrossing, separability, no dynamics. Means no dynamics. One part is that, okay, this is what you explained just right now. Is recrossing, we just ignore the recrossing, and once it is crossed, then we call it a successful reaction event.
Yes.
And I think one more point for dynamics. Yeah, means this is pretty non-equilibrium situation. Means when when it
This is a
comes
rare
from,
event.
yes, this is some distribution is coming, and it goes to the how it crossed the transition state. It is a pretty much non-equilibrium situation. So in non-equilibrium situation, the distribution function itself is time dependent.
Yes.
So they are itself in the distribution function itself, it
That is
contains
correct.
time. Yeah, means distribution function of reactant also change.
Mhm.
Okay, means if some reaction event happens, so means means strictly speaking, that accurately speaking, that distribution function of reactant will change and product will also affect.
Yes.
Okay, if one some distribution comes from this reactant side and goes to the product side. Okay, so here in this whole derivation, we also assume that those two distribution
don't change.
Yes, does not affect much because the event is rare. So one dynamics part is, I think, there means because these 3 points, yes, mean dynamics means this is this contains both. Otherwise, these two things are in the same point.
Yes, obviously, this contains actually this is replicated in the translated in the experiment the formula itself, because the TST is based on the activated process. What is activated process? Because if this reactant well and the transition well, this energy is greater than the thermal energy, then we call it activated process. So for activated process, we assume that the reactant molecules are in equilibrium here. Product molecules are also equilibrium in here, because thermal fluctuation cannot take the reactant molecules to the product side. So that's why we're assuming that the reactant molecules are in equilibrium. Product molecules are also in equilibrium. Even the transition state are also in equilibrium. Activated complex are also in equilibrium. That's why we can write this Q double dagger, right? This is from the equilibrium statement. So the assumption of equilibrium statement is also here.
Yeah, means that Q double dagger that automatically come.
Yes.
Means if we assume that QA and QB, those are in means those are still follow the equilibrium distribution.
Yes.
Means even if one few distribution goes from reactant side to product side, means as it is very dynamics contains the both the things. Recrossing plus this non-equilibrium
thing. Yeah, obviously. Actually, actually the main dynamically we have to use the focal Planck equation, how the distribution is changing.
Yes, exactly. Means that those complicated situation will come. Means if we want to means remove this approximation, then what will be the effect when we do not approximate this as a static distribution, equilibrium distribution. Then all those situations will come.
Yeah.
Okay, you can.
Okay, let me just go ahead. Okay, so this was the Eyring's thought derivation. But for actually the transition state can be an exact formula, like TST can be an exact theory, provided that we choose the transition state or dividing surface accurately. So provided transition state or the dividing surface we choose accurately, then the transition state can be an exact theory. What do we mean by this? Okay, so then comes the Wigner's phase space perspective. So which is Wigner's rule. So basically for the audience, so basically dynamics is basically happens in the phase space. So phase space basically a space of all the momentum, all the coordinates and the momentum. So it is basically QP space. It can be high dimensional or it can be 2-dimensional also. So basically for 1D system, so coordinate is just q and momentum is just p. So basically for 1D case, qp space is the phase space. So dynamics actually happens in the phase space. Why? Because if you can just take an example. So just from this point, let's say we know this point. Let's say this is q1. From this point, you are trying to throw a stone or throw a pin. But you want to predict what will be the position of the stone or pin after 10 minutes, let's say. You don't know anything about momentum, how, like with which speed, what speed you are throwing. So you're just throwing from this position. Then you cannot predict, right? You cannot derive or you cannot use equation of motion. You cannot predict after 10 minutes what will be the position of that particular stone without knowing the speed of the stone, right? So to predict accurately the position of the stone after 10 minutes or after some time, then you have to know at initial time what is the coordinates, like from which you are throwing, from where you are throwing, and the momentum or velocity, right? So these two things you have to know initially to predict after time what will happen to coordinates or momentum. So that's why the dynamics systems dynamics is actually happens in the phase space, not in the configuration space. So weaknet phase space idea was that, let's say this is a configuration barrier. This is barrier, let's say this is q equal to 0. And when a trajectory comes like this, and then when the trajectory having energy less than the activation energy, then it will go like this. Like it cannot cross classically. This is all classical. Now, when a trajectory actually having energy at the activation energy or over the activation energy, then it can cross. Right. So these are the two things. So basically, to translate this concept, so this is the configuration space barrier, and if you just draw the phase space for this, so this is q and this is the p-axis. When for those trajectories having energy, there are three regions, like energy is less than E double dagger, energy is equal to E double dagger, and energy is greater than E double dagger, right? So these are the three energy regions. So for those trajectories having energy less than E double dagger, they cannot cross this barrier, right? Then they will return from like this. So in the phase space, it will look like this. So if you go from the positive momentum, or sorry, negative momentum, let's say, so it will go like this. And here in this case also, like, so let's say this is just one side, let's drop one side. And for those trajectories which is energy greater than E double dagger, they actually can cross, right? So this is q equal to 0. That means this is the position of the barrier in the phase space. This is the position of the barrier. So for trajectories having energy greater than E double dagger, it can actually cross like this. And for trajectories equal to energy E dagger, this is the separatrix. We call it separatrix. So it will go like this. Okay, so this is the phase space. Now, let's say the barrier is here, q equal to 0. Now, let's say we choose barrier here. Okay, before this, now, if you sit on a trajectory, let's say if you sit on this trajectory, then if you dynamically, what will happen? This trajectory will not cross the barrier, so it will return. And if you sit on this trajectory, then dynamically what will happen? It will cross the barrier and a reaction will happen, right? So for each trajectory, you can assign a quantity, which is called the chi. So chi is,
Deepa,
yeah.
so what's the meaning of negative momenta here?
The negative momentum in momentum direction, because let's say momentum is absolute, like p square by kinetic energy p square. So absolute negative momentum is basically the momentum direction. So if you say reactant to product side momentum is positive direction, then you can say the product to reactant momentum is negative direction.
Okay. Yes.
So negative or positive is basically direction. So here for each trajectory, you can.
What is happening for E equals to E double dagger? So
Yes, E equal to E
Which
dagger
one?
means it will actually separate this. That means this is Q equal to 0. It will be a straight line like this. It
and
will
will
do,
not cross.
no, it will not cross. It actually, if you on the separatrix, then if you start from here to reach here at the barrier, it will take infinite amount of time. Okay.
Okay.
You can,
Okay.
you
Okay.
can analytically show this. If you start here from here, then to reach this point, it will take infinite amount of time on the separatrix.
Okay.
So separatrix actually separates the two kinds of motion, like below
Okay. Got it.
E dagger and above E dagger. So that's why it is separatrix. So on
And
each
is there any particular? Yeah.
Yeah.
Go on. Go on.
okay. So on each trajectory, you can assign one variable, let's chi, which is called the characteristic function. That means, so basically for each trajectory, this has a particular value. Like you can say if the for a reactive trajectory chi equal to 1, and for non-reactive trajectory, it's a chi equal to 0. You can give this value. So for all these trajectory, you can for this trajectory chi equal to 0, right? Because it will not, those trajectories will not cross the barrier. But for all these trajectories, chi equal to 1, because these trajectories will cross the barrier, right? So this is a dynamic quantity, and it is an invariant quantity. Why? Because the value of chi will not change on a particular trajectory, because here it is also chi equal to 0, here it is also chi equal to 0, here it is also chi equal to 1, here it is also chi equal to 1. So that's why the chi is an invariant quantity. Now let's
Is there
say,
any particular reason, Subhadip, like
Yeah.
when the trajectory for which
Mhm.
the guy goes to 1, like, which are crossing, they're
Mhm.
somehow like diverging. Is there any particular reason of that shape?
No, because of the barrier, because these things, all these trajectories have to be energy concept, like all these trajectories have particular energy E, let's say.
Mm-hmm.
So these trajectory have a particular energy, these trajectories have a particular energy E, but these two trajectories have different momentum. So you have to add
Mhm.
potential energy also. So to compensate the potential energy, these trajectories are like bending like this.
Okay. Mhm.
That's why they are bending.
Okay. Okay.
Yeah, now just to tell one thing here. So phase space looks like this, right? I'm crudely drawing this. Now let's say you choose transition state here. Let's say you are choosing, you don't have any idea about the transition state, right? So you choose the transition state or dividing surface here. Now what will happen according to the transition state theory approximation? TST,
Subhadip,
yeah.
just one quick question. Are you moving towards the contour plot of the reaction coordinate?
No.
Okay. So what are these axes?
Yeah, these are the phase space, mean coordinate and the momentum. X-axis is the coordinate and the y-axis is the momentum.
Okay, so this is totally different from the reaction
Reaction
contour
contour
plot, right?
plot. Yes.
Okay.
Okay. Let me just explain one thing. Let's say for harmonic oscillator. Okay, this is the Vx and this is x. So this is half kx square, right? So this is just the potential energy of harmonic oscillator. So you can just contour means in the potential energy is that different x value. in the 1D case. But in the phase space, what it look like? Phase space means there is two axes here. For 1D also there is two axes. One is x and one is px. Got it? So there is a momentum and there is a momentum, there is a coordinate. That means it is phase space. Phase space, what will look like this? Let's say for this energy, this particular energy, let's say E1. So what we'll do, let's say you start from here. So it will go like this and then it will come back, right? For harmonic oscillator, periodically it will do like this. It will go like this and then it will come back. So now what will happen? Let's say you start from here. Let's say you start from here. So first it will go like this, mean it is going in this direction, means momentum is negative and the x value is changing, decreasing, right? Then it is crossing this x equal to 0. Then it will going upwards. Then from this position, then it will again come back, right? In the configuration space, it will look like this for harmonic oscillator. Now in the phase space, let's start from this point. What the trajectory look like? It will go like this. Momentum is decreasing, momentum is negative, increasing, speed is increasing. That's why the momentum value is increasing, x value is decreasing. Then it is x equal to 0, reaching at this point. Then momentum is maximum because at this point, the speed is maximum. Then it will again do like this. Now it is reaching at the turning point, left turning point. Then there is no momentum, only the potential energy. That's why momentum is 0. Then it will actually then go like this, right? So this is the phase space of harmonic oscillator, 1D harmonic oscillator. So it will be an elliptical, all this energy. So all this case are for different energy. Let's say it is E1, let's say it is E2, let's say it is E3, like this. Got it, Anjali?
Yeah, clear.
Subhadip, in that case, these black figures, so those actually should be drawn otherwise, like the concave part. Suppose in this left figure, you have drawn dip in the momentum. So in that case, these trajectories are only in the product side. If you are considering momentum of reactant negative. So if you draw these otherwise, like upper arc in this positive momenta, and like you have drawn now this green one, then it's more meaningful to me, at least.
No, meaningful means it is the actual figure.
Meaningful means if you draw fully.
No, I understand. I got your point, because it is for different potential. Okay, now the potential is like
inverted. You can say
it is
inverted
harmonic oscillator.
Yes.
Now let's say for this trajectory, this type of trajectories, it is coming like this and going back. So these trajectories are translating these trajectories. Okay. This one. Now for those trajectories which are going like this, just crossing in the configuration space, these trajectories is translating this trajectory in the phase space. Got it? Now for only the one particular trajectory which have energy just the E dagger, which is this trajectory translating the separatrix.
Yeah, but in the momentum space, we are considering reactants have negative momenta and products have positive momenta. But
we are considering this, yes, we are considering this. These trajectories are going from negative momenta to positive momenta, like in this direction.
Yeah, but in the figure, all the trajectories that are above the, in first and second quadrant, they will always have positive momenta. No? That's what I was saying.
Yeah, that part is okay. You can also, you can say that this is from product to reactant. My definition was wrong. Yeah, you can compare this figure, it will be positive direction and it will be negative direction. Yeah, because here I'm showing the from positive to positive, like all these are positive momentum. So let's say these are going from reactant to product.
So actually the axes are reverted. This vertical
yes.
axis should be Q and this one should be P.
Yeah,
Yes.
you are right. So basically my point was that if you draw transition state here at this point here, then according to TST what will do? This trajectory it is crossing the transition state at this point. So according to the TST, the reaction is happening here. For this trajectory is transforming product reactant to product. All these trajectory, right? All these trajectories.
I think
But-
Subhadip, Ravi is I think confused. Means that part is means you are written plus minus P to plus P. Means for all those upper arrow curve you have just written with above the inverted umbrella.
Yeah.
Those are all plus P because always it is going in the same direction. So
Yes.
plus P to minus P, that's kind of I think Ravi
No,
does not match with that convention. It is
Yeah,
going from minus X to minus Q to plus Q. In my maximize Q equal to 0, but it is
Yes.
always at plus momentum, positive momentum.
Yes.
That thing is now Ravi. I think this is the
No, just Bansi. Actually, he has written this y-axis as momentum axis and x-axis as
yeah. That is okay. That is okay. Y-axis
No,
is momentum and x-axis Q.
yeah. Then in that case, all the explanation will not be relevant, na?
No. That's why I am
Because
telling
he is
that.
talking about that at particular Q value, at a single Q value. Now the trajectory is going from negative momenta to positive
No,
momenta.
that's I am pointing you. That's I am pointing out that trajectory is
Momentum is
not
always
going from
positive, yeah.
minus momentum to plus momentum. There
Yes.
is always momentum is always positive, but it is trajectory is crossing from minus Q side to plus Q side.
Plus Q side, yes.
This momentum is always positive. So
Okay.
you should not write here minus P. This is plus P to always plus P.
Yes.
Momentum
Here
is always positive.
I should not write this here.
Yes. Always this is positive momentum. Means
Always these trajectories having positive momentum.
Positive
Now
momentum.
for
So-
other side, product to reactant, here this you can draw like this.
Okay, so minus Q to Q is main thing. Okay, Bansi.
Yes. Okay.
Okay, so here if you draw transition state here, so according to the transition state theory, all these trajectories will give product. All these trajectories, right? But so transition state, what is transition state theory is doing? Transition state theory is overestimating the rate, because actually only these trajectories are giving the product. But if we just draw transition state here, dividing surface here, then according to the transition state theory, when the trajectory cross this barrier, like it is crossing here, we are assuming that the reaction is happening. That means the transition state theory is overestimating the rate. Okay. Now, if you draw transition state theory here, the dividing surface here, then the transition state theory will give us accurate value, because all these trajectories will not be reactive trajectory, only these trajectory will be reactive trajectory. So TST will give us accurate value. So basically the takeaway point is that the transition state theory is overestimates the rate. And the second point is that if you choose the dividing surface accurately, then TST is exact. So this was the Wigner's perspective, phase-based perspective, and I'm not going into the details because time is not giving my side.
Subhadip, just a quick question, like how to choose this dividing surface? Like how to choose this?
Yeah, there is no exact method of choosing dividing surface accurately, because there is not exact method, but there are different algorithms by which you can actually potential in the multidimensional potential in the surface, you can choose the dividing surface. Okay. Now I am not going to discuss. Okay. I will take 10 or 15 minutes extra. Is this okay?
Yeah, Subhadip.
Yes, you can.
And just one quick comment to Deepika's question. So Deepika, when in the calculation, when the slope of this potential energy surface is changing, so at that point, so they consider that is the transition state.
Yeah, that
Yeah.
is not actually what I'm doing this for the, let's say, potential energy surface. For any potential energy surface, you can obviously compute the index 1 saddle point. Index 1 saddle means there is one unstable direction and one stable direction. Let's say this is unstable direction and this is stable direction. So this is the index 1 saddle, we call it. Now, very often we actually, what we do for potential energy surface, we associate transition state or dividing surface with this index 1 saddle point. Okay. This is the index 1 saddle, and we often associate the transition state or dividing surface here. But actually, the dividing surface exists in the phase space, not in the configuration space. That's why I was not going into the details of here. In the phase space, the actual dividing surface exists. Okay, so it may be possible that in the phase space, the dividing surface is not at the index 1 saddle point. Okay, so then the TST will not give us accurate value, because easily for any potential energy surface, you can just compute index where the index 1 saddle point is. Because if you just do this for 1 decade dV dx equal to 0, then you can find out the point index 1 saddle point x equal to, let's say, x star, right? Dv dx equal to 0 and the d2 and the second derivative will be negative. Then you can find the x star, right? But often the dividing surface actually do not coincide with the saddle, index 1 saddle. It actually exists in the phase space. So then like exactly where the dividing surface is, computing where the dividing surface is a little bit of tricky. Then the TST will not give us accurate value. That was my point actually. Okay, now moving towards the next, I will not give the details here. I will just tell the main points. So basically RRKM theory. So RRKM, R stands for Rice, Ramsberger, Castle, and Marcus. So this is a reaction rate theory to compute chemical reaction rate of unimolecular reaction. Unimolecular reaction means, let's say, isomerization reaction, dissociation reactions, all these are unimolecular reactions. So to compute rates of chemical reactions, of unimolecular reaction, we generally use RRKM theory. Now, RRKM theory is also statistical theory, means it's based on the statistical mechanical analysis or statistics, basically, state counting. So the main assumption here is that the IVR is fast. That means IVR, what is IVR? IVR means intramolecular vibrational energy redistribution. So that means when if you excite a molecule with a particular energy, then that initial energy will actually, according to the RRKM theory, is very fast. Means that the initial energy will randomize into all possible vibrational modes very fast. Fast compared to what? Fast compared to unimolecular reaction time scale. Okay. So this is the main and very brave assumption. So IVR is fast. That means all the initial energy will randomize immediately into all possible vibrational modes. This was the main assumption. Here, by doing this assumption, by taking this assumption, here also we are neglecting the dynamics. We are neglecting the dynamics because so molecule, what will happen? So if you excite, let's say this is water molecule. Let's say if we excite one particular wedge bond by some energy, let's say by laser or anything. If you excite this wedge bond, it may be possible that this energy will not completely move to the other wedge mode or random or thermalize actually. It may be possible that for some time this energy is staying at this particular mode. I'm taking water as just an example. It is just 3 degrees of 3 degrees of freedom. Sorry, 3 degrees of freedom, 2 bonds. So it may be possible that my point is that it may be possible that IVR actually the initial energy may not be randomized immediately. Okay, it can get stuck in some selective particular modes. Let's say this is the overall phase space. So it can get stuck here. Then after some time it can get stuck here. So that means IVR is not fast, means intramolecular energy, that vibrational energy is not randomizing immediately, is not thermalizing immediately over all vibrational modes. It can start in some selective set of vibrational modes. Then after some time it can get stuck also some selective set of vibrational modes like this. If this happens, then when this happens, the prediction of chemical reaction rate using the RRChem theory will fail. So the basic assumption will fail. So the main point is that RRChem theory is actually neglects the dynamics. Okay, now I will show you some examples. It will be interesting. Okay, it will take almost 10 to 15 minutes. Basically, just to show this, let's say this is the phase space. Okay, let's say this is an isomerization reaction, means one well to another well. Let's say double well potential. It is doing one well to another well. Okay, basically it is, you can assume it isomerization reaction. So this is phase space. Let's say it is for the reactant well. This is the barrier. This is here is the barrier. Now let's say the phase space is completely chaotic. Chaotic means all the trajectories are behaving randomly. So in principle, the definition, chaos means sensitivity to initial conditions. Means if you take 2 initial point, let's say 2 initial point here, with time, let's say this is happy. Okay. If you take 2 initial, okay, this I cannot do this. Two initial point here. So this trajectory is doing, let's say with time this, and this trajectory is doing like this. Okay. So sensitivity to initial condition means if you choose nearby 2 trajectories, then at long time, the behavior of these 2 trajectories is completely diverging and completely different. That these 2 trajectories are very near in the configuration space or in the phase space. But at long time, the behavior of these 2 trajectories, nearby trajectories, is completely different. You cannot predict. So that's what chaos means. Chaos means the sensitivity to initial conditions. Means all the trajectories are behaving randomly. Chaotic phase space means. So let's say the phase space is completely chaotic. That means if the trajectory cross this region, then it will be reactive, means isomerization happens. So this is the RRChem model. That means chaotic phase space means so the vibration energy can redistribute over all the possible vibrational modes very randomly, like immediately. So here in this case, the IVR is fast. That's why it will RRChem model. But intrinsic non-RRChem means, let's say in the
Subhadip,
yeah.
Just a second. So these different vibrational modes are orthogonal modes.
Yes, orthogonal modes.
Yes, okay.
So in the phase space, let's say there is a kind of bottleneck. This is dynamical bottleneck because it can be any different types of structures. So here I'm not going details. So there can be region in the phase space where the trajectories cannot cross those regions. So those regions are called dynamical bottleneck. So let's say there is one dynamical bottleneck in the phase space. So beyond this region, in this region, all these trajectories can actually cross this barrier, and isomerization can happen. So all these trajectories the IVR will be random. But in this region, these trajectories cannot immediately cross this region, right? Because there is a dynamical bottleneck here. So it has to find its way to cross this region, then it will be reactive. Okay. So there will not be any and one particular rate constant, KE, because there is a dynamical bottleneck. So the rate constant will depend upon time, because there will be one rate constant for this region and another rate constant for this region, and it will also depend upon time, because trajectory has to find its way through this hole, then it will be reactive. Okay, so then we'll call it non-RRKM model. The RRKM rate equation will not give us accurate value here, because rate constant will depend upon time in this case. In third case, I'm not going to discuss here. Okay, basically, let me just go through that. Okay, basically, how do you model molecules? Molecules consist of different vibrational modes. So if we model the vibrational mode with harmonic oscillator, then bonds cannot dissociate, right? So we have to model, then we try to model the vibrational mode with Morse oscillator, or which is the enharmonic oscillator. Now the bonds can dissociate. Now here in this stage, all the classical mechanical force field we use for simulation, you notice they use the harmonic model to model the force field, like different types of force field, bond, angle. For all these cases, they use harmonic model. So why they use harmonic model? So you can ask yourself and try to find out. So basically, we have to model the dissociation. We have to model the vibrational mode with the Morse oscillator or any kind of enharmonic oscillator. So Morse, we choose Morse because the quantum and the classical analytical form of the Morse oscillator is known. So why do the molecules? And so actually molecules, so is a collection of all different vibrational modes, and all these vibrational modes are modeled using Morse oscillator. So basically, molecule is a collection of coupled nonlinear oscillator. Okay. Coupled nonlinear oscillator. Why coupled? Because all these Morse oscillator, all these vibrational modes are coupled to each other, right? And believe me, this coupling is what is making our life beautiful. So basically, coupled by non-linear coupling. Those coupling are not linear, so those are non-trivial non-linear coupling. So that's why molecule is modeled as a collection of coupled nonlinear oscillators. Now, just for simplicity, now here at this point, so to describe equilibrium structure, the harmonic model is useful, because at low energy, the potential energy actually harmonic in nature, more or less. But for high energy, the potential will become non-harmonic, right? Anharmonic. In this region, potential is nearly harmonic. So to describe the equilibrium structure, harmonic model will be useful. Now, there is another question. Organic and the inorganic chemist, or we actually, when we measure an infrared spectrum, we generally, when we interpret the spectral result, we generally use harmonic model in our daily basis, because the fingerprint region in the infrared spectrum, the fingerprint region, you know about that. For the wedge, there is another particular frequency. For CHO, another particular frequency. For CWH, another frequency. Let's say when we measure an infrared spectrum like this, when you see this is 3400, we typically assign this as wedge mode, right? when we see this is 1600, we assign this as CO mode. Now, how do we do this? So we use here harmonic model. So just think about this here. It is very important. Now, just for simplicity, let's say molecule is a collection of two harmonic oscillator. So Hamiltonian is, so basically this is kinetic part and this is potential part, two harmonic oscillator. Now, what does the phase space look like? So this is the phase space look like. This is Poincare surface of section, we call it, because for two-dimensional case, the phase space will be four-dimensional, right? Two coordinate, two momentum, so phase space will be four-dimensional. You cannot visualize the four-dimensional phase space. What is happening in the four-dimensional phase space, you cannot visualize it, you cannot imagine it. So just for simplifying the visual perspective, so if we take a particular section of that four-dimensional phase space, let's say Q equal to 0, then we are considering and P greater than, let's say Qx equal to 0 and Px greater than 0. So we are taking at a particular section of that four-dimensional phase space. So that section is called Poincare surface of section, named by the Henry Poincare mathematician. So this is a particular section. That's why it is looking like an onion ring. So this is uncoupled two harmonic oscillator. Section will look like this, elliptical. And this is coupled case with coupling lambda. This is nonlinear coupling. You can say x square y, nonlinear coupling. Coupling strength is lambda. This is for particular coupling strength. Now, how beautiful is this? The phase space is completely changed in presence of coupling. These violet are called chaotic structures. These red one are regular structures. These regions are resonance zone. Resonance means the two harmonic, let's say one harmonic oscillator frequency is omega 1, another harmonic oscillator frequency is omega 2. Now let's say if the frequency with coupling case, if the frequency ratio omega 1 divided by omega 2 is integer or rational, then it will be periodic. It will be periodic trajectory, and if the integer ratios are irrational, it will be quasi-periodic. So that we will take another lecture. So I'm not going into details. So just importantly, the structures are completely changing in presence of coupling. All these things are overlapping each other and forming chaotic structures. Then these things are distorted. This green one forming another structures. There are resonance zones here. So all the phase structures in the phase space are completely changed in presence of coupling. Now these things will eventually determine our reaction dynamics, how the energy flow will happen between different vibrational modes. These zones, these chaotic zones, this will eventually determine how the energy transfer, vibrational energy transfer will happen between different vibrational modes. Now just
Subhadip, just
yeah.
go back to that slide. And omega 1, omega 2. This is omega x, omega y means
yes, omega. Yes, omega x, omega y.
We are fixing this from initial
from our initial case.
Yes, when we are making the model. Okay.
Yeah.
So we have fixed this means whether this will be rational or irrational.
Yes.
Okay.
This is for harmonic case. Harmonic case, it is already fixed, right?
Okay.
But if you do Morse enharmonic oscillator, coupled enharmonic oscillator, then with energy, the frequency of the Morse oscillator will also change, right?
Yes, then this will depends on this energy.
Yeah, then this resonance phenomena will depend upon energy. Then the phase space is also look different with energy.
Mm-hmm.
Yep.
But for fundamental, they are also for fundamental frequency, we give the initial ratio.
Fundamental frequency
will give the initial ratio. Yes. Okay.
So basically for coupled enharmonic case, like coupled nonlinear oscillator in actual molecular case, the phase space will look completely different with different energy. So there will be different structures in the phase space. So all those structures will control the energy transfer dynamics.
Could you say more about that little bit? Little bit means this is the resonance you are showing about,
So
and
basically,
this is the chaotic. Now this upper part.
okay.
This left side spectra is normal just
Yeah, normal elliptical
that
harmonic
you
oscillator.
already plotted also.
Yes.
But right side part, this is the resonance.
Mhm.
At very means low energy, I think.
Low energy, yeah.
And this is the chaotic part when you increase the energy.
Mhm.
And
Actually, it
when
will depend upon the coupling strength lambda. Let's say we fix the lambda value
okay,
in particular value. So what is actually happening? This structure no, is actually starts overlapping with each other.
okay,
When it is coupled, it will overlap. It start overlapping with each other. So then, by overlapping, it will create a resonance zone, then chaotic zone. Then it is you look these outermost structures are getting distorted. So this will create different types of regular structures. And this is chaotic structure. Now, just to emphasize, let's say if you start here, initial point here, what will
take the other
happen?
color, take the another color. I will.
Yeah.
I could not follow. I think.
Let's say if you start from the chaotic region. So what will happen? The chaotic region means trajectories are behaving randomly. It means from one oscillator to another oscillator, energy will easily transfer. Like this chaotic region will give facile energy transfer between the two oscillators.
Yes.
This is just for two cases. This resonance case is also responsible for the energy transfer because let's say omega 1 of let's say omega 1 divided by omega 2 is 3. That means omega 1 equal to 3 omega 2, let's say. So this is a particular resonance conditions, means one oscillator equal to 3 times second oscillator frequency. In the harmonic case, I'm saying.
Yes.
That means what will happen? These condition will be responsible for energy transfer because one oscillator will lose or gain 3 quanta of energy, and another oscillator will gain or lose another quanta of energy, 1 quanta of energy, right?
Yes.
Because of this condition. So all these regions are responsible differently in energy transfer.
Okay. And this red part outside.
Yeah, red part also it will be some. Let's say it is one. These are
It shows some periodic like behavior means.
yeah, it will show some periodic like behavior. Yeah, it is not chaotic. It is regular trajectory. Means it will show periodic like behavior. Yeah.
And for that periodic like, is there any means resonance like condition means?
Yeah, I don't know actually what is the resonance condition here because this is, I think it is 2:1, 2:2. This is, I don't know, this is maybe 1:1.
I mean, higher energy resonance are there.
Yeah, higher energy resonance is also there. Yeah.
Okay, means interestingly that in between some energy there is chaotic region. So this is the
So
interesting.
these are actually at same energy.
Okay, now which one? This high energy resonance and this chaotic.
Yes, all these are same energy. These two plots are at a particular energy E. Okay, now you are looking at the section. That's why you are looking at different onion type rings. If you section a onion, क्या बोलते हैं उसको प्याज, हाँ, अगर सेक्शन करोगे तो क्या होगा, तो डिफरेंट टाइप्स ऑफ रिंग दिखेगा ना. तो सिमिलरली ये 4 डायमेंशनल फेस स्पेस को अगर तुम सेक्शन करोगे तो ये डिफरेंट टाइप्स ऑफ ऑनियन टाइप्स रिंग दिखेगा ऐसा.
Okay.
Now all these structures are overlapping with each other and starts forming different structures here with coupling.
Okay, same energy, but it depends on the energy distribution, means how the trajectory looks like. That is
different from the energy momentum distribution is different.
Momentum distribution is
Yes.
Okay. Okay.
Yeah. Okay, so just wait for some time. It will be okay. So here, just wait few seconds and just read because it is very important. So I fear you understand that's the complicated distribution of energy, dynamics of inner vibrational energy, which is getting transferred or distributed between different vibrational modes. That's called IVR. or intramolecular vibrational energy redistribution. So this is the quote from the Potter and Zbitonovic. So just read here. So in a turn of events that would have astonished anyone but Niels Bohr, we now know that the chaotic trajectories identical to those that govern the motion of comets, asteroids, and spacecraft are traversed on the atomic scale by highly excited Rydberg electrons. The almost perfect parallel between the governing equation of atomic physics and the celestial mechanics implies that the transport phenomena for these two situations is virtually identical. The orbits used to design the space missions also determine the ionization rates of atoms, chemical reaction rates of molecules. So this is the absolute beauty, like perfect similarity between the celestial mechanics and the molecular mechanics in the real molecules. The behavior structures.
Okay,
Yes.
you complete. I will just.
Yeah, no,
Okay,
just
okay. In that means, and to ask one thing that means whatever you are considering here is Hamiltonian dynamics for molecules.
Hamiltonian dynamics. This is all
but when we are talking about these single molecular vibrational modes,
yes,
is quantum dynamics means quantum mechanics effect of quantumness is much more prominent there. Means we cannot ignore it. So
no, basically
how much?
Yeah, I'm just going to. I was just going to tell, because all these are I'm saying about classical dynamics, and in this sense, the classical, or in particular the semi-classical dynamics, is more relevant to understand what is happening in the dynamics of intramolecular vibration redistribution. And quantumness, we know that quantum mechanics is actually the real theory of microscopic world. So quantum actually follow these classical roots of IVR. Obviously, there will be new roots of quantum in quantum mechanics because of dynamical tunneling.
Yes.
But quantum is will actually do follow the classical roots to flow the energy. So that is quite astonishing.
Okay. Yes.
So quantum mechanics is actually follow the classical dynamics, classical roots set up by the classical dynamics. And quantum structures will also persist. The classical structure will also. Okay, so quantum mechanics actually sense those classical structures in the phase space. All these structures in the phase space, quantum mechanics can sense that.
Means it will disperse. Means there is not the line. It will disperse around the line.
Yes. It will block, these structures will block quantum trajectory also. Like quantum trajectory, it will be wrong. The quantum mechanics also, these classical structure can block that. Yes. Obviously, there will be tunneling, but yeah, overall sense. Okay, so what I was going to tell, because so there is a term called stable chaos. So this is an article. This is an article from a celestial mechanics, an example of stable chaos in solar system. And this is an article from chemistry. Stable chaos and delayed onset of statisticality in unimolecular dissociation reaction. Just look at this two article, how similar is this? So it sounds a bit strange given the disparity between the mass, length, time scale of molecular and the celestial phenomena. But these two phenomena are quite similar to each other. So at this point, I just want to give some GAN, because we shouldn't actually look actually locally, because whatever project or whatever study we are working on has some broader implications anyway. So our job is to find, like, to connect these two phenomena, these two things. So like in spectroscopy also, every small hump is actually important, because molecules are telling their story to us. So we just have to listen, because in the gravitational wave discovery case, just a small hump in the time domain will change the whole game. So basically, we should think globally, like from different perspective. So just how the IVR become getting stuck. Let's say this is form of as the Ulam system. This is coupled nonlinear system. Just a linear, different oscillator is coupled non-linearly, 1D system. Now, if we excite one particular bond, it is seen that numerically that this energy is getting lost, getting transferred between some selective modes like this, and other modes are being spectated. So that means the vibrational energy, the initial vibrational energy is not getting dispersed or redistributed over all possible vibrational modes immediately. It is getting stuck over all these, let's say these three selective modes, and all these modes are just being mere spectator. That means IVR can get localized in some set of vibrational modes. Now, this is just a 1D system of some oscillators coupled to each other non-linearly. Now, think about what in molecule, real molecule, thousands or hundreds of vibrational modes, what will happen in that case. So now this is an organic molecule. There are NH states and there is two NH stage. The stretching frequency is close to each other, very close to each other. So there, in this case, the isomer potential energy surface has different minima, different maxima. So we are just in the experiment, they are just calculating the transition rate from one minima to another. Now, if you excite, what they saw that if you excite this particular bond or this particular bond, the rate constant is completely different. That means if you excite this bond or this bond, the energy transfer is completely different. Energy is not getting redistributed over this whole molecule immediately. So this is exciting this bond and exciting this bond is different. That means energy can get localized. So this is one experimental study, and this is an interesting study in spectroscopic community because there is there is NH and there is CO. Okay. Now there is a water molecule here. So water molecule can actually hydrogen bond to this O molecule, and what oxygen can form hydrogen bond with this H atom, right? Two possible hydrogen bonding situation. This is the settling mechanism. Let's say one time water molecule is here and another time it is water molecule is here beside this hydrogen. So this is kind of isomerization reaction, double type of reaction. One time here, another time here. So what will be the isomerization settling rate? Their question was this. Now, surprisingly, this settling rate actually matches with our RRKM prediction. That means IVR is actually the vibrational energy is actually getting redistributed immediately. Means IVR is first. Whenever water is here or there, it doesn't matter. The energy, the water or molecule complex in the water or molecule complex, the energy is getting redistributed immediately. Now there are some important ideas here. Like this is the hydrogen bonding, which is very weak. We know. Now this hydrogen bonding actually acts as a funnel to redistribute the overall energy immediately. It doesn't matter when the hydrogen is a hydrogen bonding to this oxygen or oxygen is hydrogen bonding to this hydrogen. So hydrogen bond can act as a very efficient funnel to actually redistribute energy. There are some other cases also like CH3 rotor. If your system has CH3 rotor like methyl group, this rotor can actually funnel energy, vibrational energy very efficiently. So this rotor or hydrogen bond is actually called funnel. Sorry, it is called pipe. So this weak hydrogen bond can also actually efficient redistributor of energy. So this is very important when you study the spectroscopy, any spectroscopy. So okay.
Is this a proposed theory or is there any practical experimental proof about this redistribution of this hydrogen bond?
This is experimental study. This is experimental study, and they compute the rate of shuttling experimentally. Then they compare this rate with the predicted RRKM theory, like RRKM, analytical RRKM equation. Then they actually saw that this analytical RRKM theory and the experimental rate constant actually agrees well.
Oh, okay.
So basically, I just take 5 more minutes, nothing more. So basically, when the two, classically energy transfer means what? Let's say two modes in molecule. There are 2 modes. So in water molecule, 2 OH mode are there. Classically, energy transfer means this OH mode, the OH1, let's say OH2. The frequency of OH1 and frequency of OH2. I'm talking about anharmonic frequency here, not the harmonic frequency. We are modeling this bond with Morse oscillator. So I'm talking about anharmonic frequency. So frequency of this OH mode, OH1 and OH2, the ratio of this, let's say K1 by K2 at some particular energy. When the energy will be different, this mode frequency will also be different. This resonance condition will also be different. Okay, just remember this. That means K2 times OH1 equal to K1 times OH2. Right here. This is the resonance condition. That means the OH1 mode will gain or lose K1 quanta of energy. OH2 mode will gain or lose or gain K2 moment of quanta of energy. Classically, this energy transfer happen this type of resonance condition. Now, for 3 modes, there will be one condition here, like N1 omega 1 plus N2 omega 2 plus N3 omega 3 equal to 0, like this. Like for 4 modes, there will be another condition like this. Classically, now quantum mechanically, what does this mean? Quantum mechanically, this resonance, classical nonlinear resonance, is actually translate quantum Fermi resonance. Probably. So this will take another, it will be very interesting. So classical resonance and the analogy between the classical resonance and the Fermi resonance. So these resonance condition will actually transfer to the Fermi resonance in quantum mechanics. Okay. Now, all these condition, 3 modes, 4 modes, all this resonance condition in the high dimensional phase space will create this type of zones, this type of lines. Okay. All these structures. Actually, what it will look like, this is called actually network of nonlinear resonances. So the phase space of a whole molecule is populated with this network of nonlinear resonances, and trajectory will follow these resonance structures to transfer energy between different vibrational modes. This network of nonlinear resonance is called the Arnold wave, named by the Vladimir Arnold, a mathematician. This is actual picture. Look at the intricate structures here. All straight lines, all these regions of different resonance conditions, like N1 omega 2 plus N1 omega 1 plus N2 omega 2 equal to 0. This type of resonance structures, resonance condition, all these structures. These area are called junction, because here 2 types of resonance structures, it's a different types of resonance structures that actually connecting at this point. So this is called junction. At the junction, the dynamics is very different. So this is the actual picture, classical mechanically. But quantum mechanically, what will happen? Quantum mechanics will also follow or also sense these routes, this network of resonances to transfer energy. Additionally, there will be tunneling also. This is called the dynamical tunneling. What is different from tunneling and dynamical tunneling? Tunneling in the sense of configuration space, because if there is a barrier, then molecules can tunnel from one side to another side. You know this, like configuration space tunneling, quantum mechanically. Dynamical tunneling means even in the absence of any barrier in the configuration space, there can be structures in the phase space which can block the trajectories classically, but quantum mechanically it can tunnel from one region to another region. That's why it is called the dynamical tunneling. And because of this dynamical tunneling, in the high resolution spectroscopy, you can see different types of splitting. All this splitting can explained by this dynamical tunneling phenomena. This is very important. In my last slide, from dynamical properties from the bias sampling, actually in the bias sampling, metadynamics or umbrella sampling, we generally, after computing the free energy surface, we generally use the TST, transition state theory, to compute the rate. Because we know the barrier energy delta G double dagger, so we just use K equal to KBT divided by H and e to the power minus delta G dagger divided by KBT. We just use this equation using the value of delta G double dagger and get the rate constant. But just remember, this is done using the TST without including the dynamics. So often it can get misinterpreted. So I am, from my experience right now, I am experiencing these things because all different experimental papers is actually reporting some nonsense rate constant using the TST from experiment. So there are many different methods are there to compute, calculate rate constant, actual accurate rate constant from the bias sampling. Like infrequent metadynamics is very famous, which can compute rate from metadynamics to dynamics. So then transition path sampling is there. Also many more methods are there, which are very popular. Okay, so the main takeaway message is that vibrational energy transfer dynamics is very complicated, but in some sense it is very simple. We have to understand these dynamics to understand the mechanism, and then to control over the mechanism, to control the reaction. And when you use the popular rate equations or rate formulas, just read some assumptions or some details so that you are aware that what you are neglecting. So it is important actually. Okay, so I am done. Thank you for this, and thank you for paying attention.
Subhadip, just
Yeah.
go to that Arnold part.
Okay.
There are these space you called, this is the Poincare section, or just go to that.
Yeah.
Just
This-
above that. Yes. That Arnold wave contour. This is the
suppose this YOLO.
now
YOLO.
what is, yes, means what is X and Y?
Oh, this is actually frequency ratio. Let's say we have 3 modes here. Let's say this is just for, let's say, ozone water molecule. Let's say water molecule, but water molecule. Let's say. So this
Okay.
is like 3 frequency are there, right? It is omega 1, omega 2, and another bending frequency. Okay. So this axis, let's say omega 1 by omega 3, and this axis, let's say omega 2 by omega 3, like this. So this is the
Okay.
axis frequency ratio.
This should be rational.
This should be rational or integer. Yeah.
Okay, and go to the above slide. One more, yes. And here, if this K1, K2 OH1 equal to K1 OH2, that means if we write that expression like this equal to 0, so one should have negative value, means N1 or N3. Means, is it correct, or all the N1 into N3 could be positive? Means
no, all the integer values should be positive. Yeah.
Integer value, but here if we convert this expression K1 OH1 equal to K2 OH1 equal to K1 OH2, there K1, if we convert it like K2 equal to N1 and N2 equal to minus K1. So that is understandable, means when N2 equal to K2 and means one is positive and one is negative.
Yes.
In that sense, but when both are positive, then how do we think the physically that expression?
No, basically, no, ratio will always be positive, right?
If ratio is always positive, then I think at least one integer value would be negative.
Yeah, like for this condition, like sorry. like for this 3-mode condition.
Yes, yes.
Okay, so 3-mode condition basically say n1 omega 1 equal to minus n2 omega 2 minus n3 omega 3. So the ratio of minus n3 minus n2 by n1 is positive. Okay.
Okay. Means
It is
yes. Means
positive.
yes. Means one should be negative. Means
Yes,
otherwise
one should be negative. Yeah.
one should be negative. Otherwise, this negative frequency will not work.
Yeah. To match this condition, yeah, one should be negative. Yeah.
Yes. That is for confirmation. Okay.
Yes.
Mhm.
Okay. So sorry for taking away one beautiful Sunday evening. Hopefully you get something.
No, this is important. Means you remember that we are trying to capture this Fermi resonance. Means
Yeah.
this Fermi
Yes.
resonance.
I also trying to compute that. Yeah.
Yes, we tried, but we could not succeed. And that is means I think the knowledge of this kind of thing means we are always taking into account the means harmonic like region, means small amount and anharmonicity, but this is perturbative treatment, just like Skinner did. So we have to not think like that. This is the another different regime. We could not think like perturbative sense when we are when we try to deal with this Fermi resonance. Because this is a strong resonance between this overtone bending and fundamental stretching. So perturbative expansion of the stretching would not help at all. So
no.
So this kind of knowledge is required there. It's how to deal with that. Means we have to deal with in another with another modeling basically.
Yeah.
So this is important discussion. So
Actually, it's very exciting. Like one day I was reading what is the analogy between the classical nonlinear resonance and the Fermi resonance. So there are many details is hiding here. So it is very important.
Yes. Classically, we have also some kind of resonance, but
yes.
But quantum mechanically means we restrict the level.
Yeah.
Okay, means we quantized the level, and so there is not continuum like thing as classically we can see. So means classically there should be some correspondence, but I don't know means how
actually
how close they are.
Just to extend actually quantum Fermi resonance means what is like we have a psi1, we have a psi2. Energetically they are similar, like they are near to each other. Then these two psi are coupled, and then by it will create a two cross two Hamiltonian, and by diagonalizing these two Hamiltonian, it will create two states. These are two. These are called this is the mechanism of Fermi resonance, right? So classically, what will happen classically, that if you start classical state corresponding to the psi1 and corresponding to the psi2, those states which are participating in Fermi resonance quantum mechanically, classically you will not see any resonance phenomena. But if you start classical state corresponding to the off-diagonal element of psi1 and psi2, then you will see the nonlinear resonance condition corresponding to the Fermi resonance, which is a great condition, because I didn't fully read the article. So there is a full article of Polanyi.
Okay.
Which is very interesting.
So how to classically capture this phenomena.
You can visually observe the Lissajous figure in the classical mechanics, like configuration figure corresponding to different Fermi resonance. You can visually see that.
Yes. We should look into that, and if we can extend the Skinner's into there, because those are not those formulation are not there. For other kind of non-trivial resonances.
Those are important, because interpreting those tiny peak response to this. Yeah. Okay, so any questions you can have, any doubts you can just ask. Sorry again, sorry for the late. It's almost stretching 2 hours.
It is natural, it will be stretched.
So no questions? Okay. So next week is going to present.
Okay, I just stop sharing. I just stop sharing if
Yes.
there is no question.
You can stop recording also.
Stop recording, yes.